constructed in the private sector. Right here, we have corner columns. Those columns were larger than any columns that had ever been put into a building before. And they're in pairs. There are two columns. And they're steel columns, obviously. And this is what one of them looks like. So it has a 100 millimeter thick plate here, and 200 millimeter thick plate in the center. Well, 200 millimeter thick plate has a problem in that, at that time particularly, it was difficult to get the high strength of steel. So we came up with another idea. We said, okay, we'll make a kind of hybrid design where we wrap the column with high strength steel, and in the core, in the center of the column, we use low strength steel. We kind of fool the column into thinking all of it's built out of the high strength material. In fact, the reduction in strength because of the lower yield point of the center material was very, very small. And to give you an idea of the scale, this is what a concrete column would look like, where the reinforcing steel is made out of 50 millimeter diameter reinforcing bars grouped into bundles of 4. So each one of these is 4 50 millimeter diameter bars. So you see, along with this comes a huge increase in the overall efficiency of the building itself. And by the way, a very significant improvement in the time of construction. And then lots of other things. The United States Steel Company at that time had the largest privately owned air force in the world. Not a military air force, a private one. So the building was designed for not just airplanes or helicopters, it was designed for vertical takeoff jet aircraft. Now, I have to tell you, no vertical takeoff jet aircraft has ever landed on the roof of this building and probably never will. But when I was in the Navy in the Second World War, I took off on a DC-3. It's pretty old, a DC-3. I don't know if they fly anymore, in an airfield smaller than this one. Very big building. Now, beyond these very tall buildings, we also do little buildings, and I'm again trying to show you something about the relationship between the architect and the structural engineer. For this project, we were the engineers for the concept or the schematic design for the museum, and we were the engineers for the bridge that connected the museum to a tunnel that went back to a parking area. Now, the bridge is unusual in that it is, we call it a post-tension steel design. That is, each one of these cables is stressed with hydraulic jacks. So the bridge was built low, and then with the hydraulic jacks, each of the cables stressed to bring it up level again. And the largest structural member in this bridge is a 125 millimeter diameter pipe. Now, sounds good, but when we got around to sorting out the size of the drain pipes, because on a bridge you cannot just let the water dump off the edge, you have to collect it. The drain pipes were bigger than the structure. So we battled that problem in various forms and ultimately came up with an idea for a permeable bridge deck. That is, this surface right here is porous, so that the rain comes in at the top and rains out the bottom. So there are no drains in the bridge at all. We were not the total designers of the bridge. We did not do the lighting, for example, nor did we do the handrail. Handrail was done by IMP. The quality of construction in Italy is nothing less than fabulous. You can get the very best workmanship on the planet in Japan. And those of you who know about steel construction will appreciate that each one of these is a casting and each one of these is a pipe. And they fit together perfectly. You cannot find the seam after they are welded. We could not do that in the United States, and I'm not sure about Italy, but we certainly could not do it in the United States. Now, there's another facet of the architect which is different from that of the engineer. The architect, IMP, and I were standing at this end of the bridge looking across it, and right here was a big concrete slab laid back against the earth. And I said to Mr. Pei, I said, wouldn't it be much nicer if just the mouth of the tunnel came out and we didn't have that concrete slab? He said, yes, it would be, but we needed it for erosion control. I said, no, Mr. Pei. That's not erosion control. That's your design. He marched across the bridge and said to the contractor, take it out. And so they demolished all this and later planted it, so today you cannot find its presence. People have also asked me, well, what is the shape of this arch? Where did it come from? Is there some wonderful mathematical derivation? And I say, no, I just sketched it one day and I liked the shape and that's the one we use. There's no reason why it has to have a mathematical precision to it. If it's handsome, go for it. And then this where the post-tension tendons strike the tunnel is a circle. This is a sort of a free-form shape. And of course, this is a straight line. So the cables, when they come down, describe this kind of spider web feeling, which when you walk out of the tunnel onto this bridge is wonderful. And then the only part of the tunnel that we really designed was the shape, because this is a non-mathematically defined shape of the cables. And we set the inner face of the concrete of the tunnel so that it was equidistant from the cables. And then to sort of finish it off, we imagined some imaginary cables. And so the mouth of the tunnel has a kind of bell shape. That is, it rounds and then it flares out a little bit at the bottom. Now, we had opening day. It was in November. It was a lovely day. And this tells you something about the culture of Japan. I cannot speak to Bergamo, but compared to the culture of New York, the people were told when they get to the gray line, they should stop. Now, you could say that to people in New York, but to get them to actually stop would take 3 lines of policemen, barricades, and so forth, but the Japanese are much more disciplined, and they in fact stopped right there. And also, in New York, the structural engineer would be under the bridge, not on top of it. So in the museum itself, Mr. Pei provides the shape of the roof, and we provide a structure inside. Now, it is a cooperative effort. That is, we propose a structure, and we work together a lot, so we're always successful. But IMPE has, if you will, the right to veto over our proposals. So all of this structure that you see is something that we proposed to him, and he liked it, and so we built it. And I can show you many structures where, in fact, that is the case. Now, it is a kind of space frame structure, and I show you this one because I think it is particularly homely. That is, it is not a handsome connection. Too many pieces coming, too complicated, but fortunately there are only 2 of these, and the rest of them are much better. But again, you see something about the workmanship. There's this piece, and back to about here is a casting, and the rest of it is a pipe. And it is all finished and painted so that it is perfectly smooth. And we designed some special bolts to put it together, and I think quite successful. And then working with the same architect. This is a concert hall in Dallas. Those of you who are into American politics, U.S. politics, I should say, because America is both North and South America. U.S. politics, Ross Perot was the one who put up the money for this, most of the money for this building. And these concrete girders that go around here are all held up with post-tension tendons buried inside of the mullions. But the question came up with the glass design in this area. And here the mullions are vertical and they keep getting more and more sloped until out at that end they're about 24 meters long. And I said to Mr. Pei, I said, well, each of these in the wind is going to deflect a little differently, and the glass is going to flutter. It's not going to pillow, but it's going to tip back and forth, and you're not going to like it. He said, what can I do about it? And I said, well, you need something that integrates all of the structure into one system. We call it bridging. He said, fine, what does it look like? And not wanting to prejudice him, I drew a diagonal line across the glass. He said, that's fine. And like 2 minutes later, he came up with this design. I could never have done that. Never. And this is an interior view of the same space. And each one of these are the structure we've been talking about, and the ones going the other direction are the bridging pieces. And notice that you can see them, but you can't quite see them. And I have an advice to those of you who are either architects or engineers, or if you're a bit of both, and that is, whatever you design, try to make it beautiful. Even if it's covered up so that you can never see it again, try to make it beautiful. So when you do see it, or you take your family to see it, your friends, you're proud of what you did. And when you're all through, you'll find out that in the long haul, the more beautiful structure is usually the least expensive and the most efficient structure. Now, we do lots of little buildings. This one is a room for a family, a single room. And interesting enough, the most challenging part of this whole project was how to wash the windows, because this is in the United Kingdom, and there, in that particular part at least, is necessary for the cleaning lady to be able to get to the windows and wash them herself. So inside this space, we had to get the cleaning lady up to here so that she could wash the windows. And so we devised this simple little piece of equipment that would put her up there so she could wash the windows. And I've been told it's never been used. That is, professionals go in and wash the windows, not the cleaning lady. But again, the structure inside is something that we propose, and Mr. Pei likes it, almost always likes it, and so we build it. This is in New York City, an inner courtyard. We were the structural engineers for the building, which is towards the street, and on the left is what we call a building which is protected. That is, you're not allowed to change it, at least only superficially. And the architects wanted to use an arch that went from here up and over to the existing building. Now, this building was done in the turn of the century. There are no drawings of the building available. Probably there were then. But even if there were drawings, you wouldn't trust them to show which is actually in place. And so we were very reluctant to take the thrust of the arch into the existing building. And actually, Satine, who is sitting right here in front, is the one who proposed this structure. That is, we build a truss. It's a plane frame truss. It has no three-dimensional characteristics. It's a two-dimensional truss. We build them in pairs, and we tip them together so that they almost, but not quite, touch. And it produces simple, elegant, inexpensive roof structure. And prize-winning structure, by the way. In Berlin, again now with IMP, we did the design for the Historical Museum. And our commission was, unfortunately this slide is cut off a bit here, but our commission was for the metal and glass structure that is on two sides of the building. This part right here is a cone, but it's not a regular cone. The tip of the cone is offset, so that no two pieces of glass in this space are the same. And it's twin glass, made of two pieces of glass, just a few millimeters apart. And I said to Mr. Pei, I said, what's it going to look like when you look diagonally across this cone? You're going to be looking slantwise through four different pieces of glass. He said, don't worry. And he was absolutely right. It looks wonderful. But then how to build it? Where are you going to get people to make glass with this kind of tolerance? And interesting enough, it came from Italy. So the Germans very reluctantly accepted imported glass from Italy. The inside structure is just that. That is, there's no cladding on this structure. You're looking at the bare steel structure. And here you see the staircase being fabricated. This section that doesn't look like it, but it's a kind of a cross-shaped structure.